Membrane pervaporation is commercially employed for separation of water-alcohol mixtures. The membrane layers could be constructed of zeolites such as DDR, chabazite, faugisite, LTA, or ZIF8, even copper BTC. The membrane fluxes of water and alcohol are governed by both mixture adsorption equilibrium and intracrystalline diffusivities of the guest molecules, water and alcohol, through the microporous crystalline layers that are typically less than about 50 micrometers in thickness. In this presentation, we examine the characteristics of the adsorption of water and alcohol in such microporous materials. The aim is to stress the possibility of molecular clustering due to hydrogen bonding. In these 6 graphs, I plot the unary isotherms for water, methanol, and ethanol, indicated by the red circles, green squares, and blue triangles for 6 different microporous materials: chabazite, DDR, ZIF8, all-silica faugisite, all-silica LTA, and copper BTC. All the isotherms have been determined using configurational-bias Monte Carlo simulations at a temperature of 300 Kelvin. For all host materials, we note that the isotherms for water in particular have very steep characteristics. For example, you see a steep rise in the loadings of water for chabazite, DDR. Indeed, for all host materials, we see that the isotherms for water are particularly steep. And we ask the question, what causes the steepness of the water isotherms? To gain further insights into the unary isotherms characteristics, let's focus on the unary isotherms in DDR zeolite. DDR consists of cages that have a volume of 278 cubic angstrom. Each cage is separated from adjacent cages by narrow 8-ring windows whose dimensions are 3.8, 3.6, 4.4 angstroms. The unary isotherms are plotted here, and to gain further insights, I calculate from the unary isotherms the inverse thermodynamic factor, 1 divided by gamma, which is defined as the partial of ln q, q being the molar loading, divided by the partial derivative of ln f, which is f is the partial fugacity in the bulk fluid phase. For the simplest case, in which the unary isotherms are described by a single site, a Langmuir isotherm, 1 divided by gamma is equal to 1 minus theta, where theta is the pore occupancy. In other words, 1 divided by gamma can be identified as a parameter that quantifies the vacancy. So we take these unary isotherms and determine the 1 divided by gamma for each of these isotherms by differentiating the isotherm fits, which are described by the dual Langmuir-Freundlich model for each of the guest molecules. The values of 1 divided by gamma are plotted against the pore occupancy. In this graph, we note that for methanol and ethanol, 1 divided by gamma decreases with increasing pore occupancy. In other words, the vacancy reduces with increasing pore occupancy, as one should expect. But the behavior of water is completely different. For pore occupancies less than about 0.3, we note that the inverse thermodynamic factor increases in value to about 3.2 before it finally reduces to 0. Now, how do we interpret a value for the vacancy that is larger than unity? This seems to be incredulous. Let us examine this a little bit further in the next slide. In this graph, I plot the inverse thermodynamic factor for water in 5 different host materials: faucesite, LTA, chabazite, DDR, and ziphate. For all 5 hosts, the 1 divided by gamma factor has values exceeding unity for pore occupancies below about 0.3. So let us try and explain this by means of a checkerboard representation of the number of sites available within a microporous crystalline adsorbent material. I consider 2 cases. On the left-hand side, I have a checkerboard with 64 available sites that are occupied by 10 unclustered molecules represented by these red circles. So the occupancy is 10 divided by 64. Let's now consider a scenario in which we have molecular clustering. Say in the case of water, this clustering could be due to hydrogen bonding between the pairs of water molecules. And let's assume that the adsorption of water is represented as the adsorption of dimers. So if these 10 molecules are all clustered, then the clustered species, each of the 2 molecules cluster together, and this dimer will occupy 1 adsorption site. So if cluster formation occurs, the occupancy, pore occupancy, is 5 divided by 64. In other words, 59 vacant sites are available for further adsorption. even if no further clustering occurs, and additional water molecules do not cluster, then a simple arithmetic would lead to the conclusion that we can additionally allow the occupancy of 59 additional water molecules. So 59 plus these 5 sites, these 5 sites are occupied by 10 molecules, so 59 plus 10 is 69. So if there's cluster formation, I can allow 59 plus 10 equals 69 molecules to occupy 64 sites. In other words, if clustering occurs and I have only 5 dimers and 59 monomers, I have 59 plus 10 guest molecules, that is equal to 69 molecules that can occupy 64 sites. In other words, the vacancy is effectively increased due to cluster formation. So the conclusion we draw is that 1 divided by gamma is a measure of the effective vacancy, and values exceeding unity signify the occurrence of cluster formation. And this leads to steep isotherms. Put another way, steep isotherms for water are caused due to molecular clustering, in this case hydrogen bonding between pairs of water molecules, and this leads to an increase in the effective number of sites that are available for adsorption. In a follow-up presentation, whose name is Cooperative Mixture Adsorption, I demonstrate that molecular clustering and hydrogen bonding results in a phenomenon of cooperative mixture adsorption. Due to a strong hydrogen bonding between water and ethanol molecules, the component loadings of water for mixture adsorption, shown by the red circles here, are significantly higher by about 1 to 1.5 orders of magnitude than the component loadings for pure water. This is the consequence of enhanced water ingress due to the fact that the water molecules are bound to ethanol molecules due to hydrogen bonding, and they ride piggyback on the ethanol and gets co-adsorbed with ethanol. This phenomenon, in which the component loadings in the mixture are higher than the pure component loadings compared to the at the same partial fluid phase fugacity is called cooperative mixture adsorption. And this phenomenon is observed not only for DDR zeolite, but for chabazite, ziphate, faugisite, and LTA. And in this graph, I plot the enhancement in the water loading, that is the component loading for mixture adsorption divided by the component loading for the corresponding unary system as a function of pore occupancy. And we note that the enhancement can be about 2 orders of magnitude depending on the pore occupancy. The IAST fails to capture quantitatively the enhancement in water loadings because the IAST does not cater for molecular clustering effects due to hydrogen bonding. Having gained insights into the water-alcohol mixture adsorption in zeolites such as DDR, chabazite, LTA, faugisite, and ziphate, let's turn our attention to water alcohol pervaporation across a zeolite membrane of thickness delta. Here is a schematic of a membrane permeation unit. The upstream compartment has partial fugacities of components 1 and 2, water and alcohol. The component loadings at the upstream face of the membrane are Q1 and Q2. The corresponding component loadings at the downstream face of the membrane are Q1 delta and Q2 delta. The expression for the transient development of the component loadings of water and alcohol across the membrane are described by this partial differential equation, where Qi is the component loading of species I at any position Z and at time t in the membrane. Ni is the transmembrane permeation flux, and Z is the distance along the membrane from the upstream face to the downstream face. Rho is the framework density of the membrane layer. The fluxes N1 and N2 for water and alcohol are related to the gradients of the component loadings by the Maxwell-Stefan diffusion equations written here, where d sub 1 and d sub 2 are the Maxwell-Stefan diffusivities of components 1 and 2. In addition, we have a two-dimensional matrix of thermodynamic correction factors. These factors are of paramount importance in the modeling of water alcohol permeation across zeolite membranes. The elements of this matrix of thermodynamic correction factors can be determined using the real adsorbed solution theory. For background information on the Maxwell-Stefan diffusion equations and the use of the RAST to describe water alcohol mixture adsorption are described in these two publications of mine. Watch also other video presentations that describe diffusion in ordered crystalline microporous materials, the RAST for mixture adsorption, and transient mixture permeation across microporous membranes. All these videos are available on my YouTube channel. Let's examine the elements of the matrix gamma for the specific case of a 595 water ethanol mixture in DDR zeolite. The continuous solid lines, red and blue, are for water and ethanol. These are the diagonal elements, and the off-diagonal elements gamma 12 and gamma 21 are shown by the dashed lines. The correction factors are plotted against the total fugacity in the bulk fluid mixture. At very low occupancies, the cross coefficients are both 0, but as the pore occupancy increases, the off-diagonal elements are of significant magnitude. Indeed, at a total fugacity of 100 kilopascals, the cross coefficients or off-diagonal elements are significantly larger than unity. Indeed, for the gamma 12 coefficient is larger than the diagonal gamma 11. Now, the significant off-diagonal elements contribute significantly to the membrane permeation fluxes, as we shall see in the following slide. For the specific case of pervaporation of a 595 water ethanol mixture permeation across a DDR membrane, this graph presents data on the transmembrane permeation fluxes for water and ethanol as a function of time. Indeed, instead of the time, we plot square root of the time on the x-axis. The continuous solid lines are for the permeation fluxes determined using a model that takes proper account of thermodynamic coupling effects. The red line is for water and the blue line is for ethanol. The dashed lines are the corresponding flux calculations using a model in which the thermodynamic coupling effects are ignored and the elements of gamma ij are taken to be the Kronecker delta. We note that in the scenario in which the thermodynamic coupling effects are duly accounted for, the water permeation flux exhibits a pronounced overshoot, and this overshoot disappears if we follow a scenario in which thermodynamic coupling effects are ignored. Another important point to note is that the ethanol permeation flux is significantly higher when thermodynamic coupling effects are included, and if thermodynamic coupling effects are ignored, the Maxwell-Stefan model significantly underestimates the ethanol permeation flux. So the message to emerge from these calculations are, firstly, the mixture adsorption equilibrium needs to be determined using the RAST. Thermodynamic coupling effects are necessary for inclusion in the membrane permeation model, And if thermodynamic coupling effects are duly accounted for, the water flux exhibits a transient overshoot. Ignoring thermodynamic coupling effects severely underestimates the ethanol permeation flux. These conclusions can be found in my paper published in 2016 in this article.